the Chapter 4 review. Number 1, according to the article on the Guardian website, women born 2003 have a 27% chance of living at least 100 years old. Okay, so suppose you select 200 women who were born. Will exactly 54 of them? Okay, so 54 is exactly 27. Okay, so if I take 200 women, will exactly 27% of them live to be at least 100? No. 54 would be exactly 28 to 27%. But if I select a random 200 people, it's not a guarantee that it will be 27% or 54 people. It's probably going to be close, but not exactly. The 27% probability is in the long run over many, many, many people, not just one group of 200. Part B, 5 high school friends all happen to be females born in 2003. Assume they're independent of each other. What is the probability of at least one of them will be 100? So this is the idea of at least one. So at least one, okay, would be, I want to add up 1 plus 2 plus 3 plus 4 plus 5 of the friends. But what we're going to do is we're going to use the complement. Okay, so we're going to use 1 minus probability of none. So the probability that they live to 100 would be 27%. So the probability that they don't live to be 100 would be 73%. And we want, for none of them to live there, we want all 5 of them to not live to be 100. Okay, so it would be 1 minus this, which would give us this. So if I add 1, 2, 3, 4, and 5 all together, it comes up to be 79%. Okay, number 2. Okay, what kind of vehicle? Choose a new vehicle sold in the United States in 2014. Probability that it's a car or a pickup or an SUV or a crossover or a minivan. Crossover, once again, all these have to add to be 100%. So 100% minus these others give you 24%. Okay, number 24%. Okay, part B, given that is not a passenger car. So once again, this is the given part, so we're only looking at those that are not passenger cars. So passenger cars are 46%, so I'm looking at the other 54%. So out of 54%, what's the probability of a pickup? So it's 15% out of the 54%. Okay, we're not using that group. We're only using these others here. Okay. Part C, what is the probability the vehicle is a pickup truck, SUV, or minivan? Okay, so when we think about or statements, we're going to add them together and just subtract any overlapping, but there's no overlapping here. So pickup, SUV, or minivan, add them together is 61%. Okay, part D, suppose you select 3 at random. You want to know the probability the vehicles are 3 different types. Describe how you would carry out a simulation. Okay, don't actually have to do this, you actually just want to describe the simulation. So I'll get 100 pieces of paper, identical pieces of paper, write passenger on 46 of them, because 46 out of 100 would give you that 46% there, right? I would write 15 pickup truck on 15 of them, SUV on 10 of them. Crossover was, what did we say, was 24%, so 20 crossover on 24 of them, and 5 minivans. Okay, so put them all into the container and mix them up, and I would select 3 pieces of paper representing the 3 vehicles selected. Okay, you could also use a random number generator. So you could say, just make 24 of the numbers crossovers, 5 of the numbers minivans, 10 of them. Okay, and you can randomly choose 3 individual numbers. That'd be another way you could do it. Okay, number 3. Suppose one subject from this experiment is selected at random. Probability they preferred C. Okay, so C, how many people chose C? Be 24 of them, right? So what I did was I kind of went to the totals first. Okay, so I got all these different totals here, and I think that makes it a little bit easier. So C was 24 out of the 94 people. C or F, okay, so C or F. Okay, so I can add different ways you can do it. You can add all your C's together, which was 24, and then add all your F's together, which was 36, and then subtract these 13 because they were counted in both groups. We don't want to double count them, so we get this answer. You could also just add these together and that together and just count them together. You get 47 of them. Okay, C, given F. So given F means we're only looking at these 36 people. We're ignoring the males. Okay, only looking at the females. So out of the females, out of those 36, how many were C? 13 out of the 36 were C's. Okay, number 4. We got Mike's Pizza Shop. There were 7 pizzas in the oven. 3 of them have a thick crust, and 2 of the 3 thick crusts have mushroom. Of the remaining pizzas, 4 pizzas, 2 have mushrooms. Okay, so Venn diagram here. So I kind of wrote this stuff down here as I was reading through it. I kind of wrote some stuff down, and then I went into this. So thick crust and mushroom, they're going to overlap because some are both. So out of the thick crust, there were 3 pizzas, and 2 of them had mushrooms. So here's the mushroom too. So 2 of them were thick crust and mushroom. That leaves the third one, the one of them that is only thick crust and not mushroom. And of the other 7, okay, well, there's 4 left that were in here, right? 2 of them had mushroom. So, hold on, let me look at something quick. Yeah, it says of the remaining 4. So there's 4 pizzas left, 2 of them have mushroom. So 2 of them are only mushroom and not the thick crust. Okay, 2 of these were thick crust, 2 of these were only mushroom, which leaves 2 pizzas that were not thick crust and that were not mushroom. Okay, so part B asks us, are the events independent? Okay, getting a thick crust and getting a pizza with mushrooms, are they independent? So if they're independent, we have to check for this. Getting thick crusts is at the same probability as getting a thick crust given that it was mushroom. Okay, so thick crust was 3 out of 7 of them. Now if we look at only the mushrooms, there were 4 pizzas with mushrooms, and 2 of them had a thick crust. So knowing that it had mushroom on it had an impact on whether the probability that it was going to be a thick crust pizza, because 50% of the mushrooms have thick crust, and let's see, what's 3 over 7? 0.43. So of the mushroom pizzas, half of them were thick crust, and overall 43% of them were thick crust. So that they're not equal, therefore not independent. Okay, knowing it as mushroom has a higher probability than if it was just a thick crust. Okay, so the next one said, what if you add part C, add an 8th pizza to the oven. This pizza has thick crust with only cheese. So if it's thick crust with only cheese, then we're going to have to add another one here, right? So it's 2 here. So now, are they independent? Okay, getting a thick crust would be 4 of them out of the 8, which would be 50% of them. And in the mushrooms, 2 out of the 4 are thick crust. So they're both equal. So since they're both equal, we know they're independent of each other. Doesn't matter if they're the same probabilities. Okay, number 5. Socks in a drawer. He doesn't pair them up before he puts them after he washes them. So one morning, he opens his drawer and just picks 2 random socks out. In there are 8 blue, 6 brown, 4 gray, and 2. He's picking 2 of them. Okay, probability they're both blue. Okay, so the first one is the probability it's blue would be 8 out of the 18. And if he already picked a blue one out, he would have 7 out of the 17 left that were also blue. So blue and blue, multiply them together, you get about an 18.3% chance he's going to get 2 blue socks. Okay. Part B, what's the probability that they're the same color? So they're the same color if they're blue blue, or brown brown, or gray gray. Okay, so you can think of it as a chart here. Blue was 8 out of 18, and then the second one would be 7 out of 17, right? We found that one already. Brown brown would be 6 out of the 18 are brown, and then after I picked a brown one, another brown one would be 5 out of 17. Okay, if I multiply those together, I get this. And a gray gray. The first gray would be 4 out of 18, and then the next gray would be 3 out of 17. Okay, so those, all 3 probabilities, add those together, 32% 32% chance they're going to get some matching socks. Okay, number 6. Company developed a drug test to detect steroid use by athletes. The test is accurate 95% of the time when they have taken steroids. So if they have taken steroids, they're going to test positive 95% of the time. It's 97% accurate when they haven't taken steroids. So if they have not, they're going to get a negative result 97% of the time. So let's suppose the drug test is used in a population of athletes where 10% have taken steroids. So we're saying that 10% have taken steroids, which means 90% have not. If they've taken it, they're going to test positive 95% of the time, 5% of the time not. If they have not taken it, they're going to test negative accurately 97% of the time and a false positive 3% of the time. So the first one says, what's the probability they're going to test positive? So if you multiply there, and multiply there, add those two together, those are the ones that are the positive results. So there's a 12.2% chance they're going to get a positive result. Okay, now the next one, of those that tested positive, what percent of the time are they actually people that have used drugs or the steroids? So of that group, right, if we're looking at this group and this group, of the people that test positive, which was 12.2% of the time, what percent used? Okay, so used was that. So that divided by that is about 78% of the time. So about 78% of the time, when somebody tests positive, they will have actually used steroids. Not a very good test. I would want that to be higher. You could also think of it this way. This would be a good follow-up question. What's the probability that somebody tests positive if they have not taken steroids, right? We don't want to actually, what's the probability they would test positive twice in a row? So that would be 0.027 times 0.027, so 0.027, that is 0.0007. So what you would have to do is, with a test like this, since there's so many false positives, is test somebody twice if they test positive, and if they test positive twice, there's only test positive and not taken, there would be a very slim chance that they would have not taken steroids if they test positive twice. So you just have to do a second test with a lot of false positive and negatives. Okay, number 7. So we have a 16-sided die. Okay, that's a very different die. The outcome of chance events, anywhere from 4 to, okay, so anyway, we have a 16-sided die. We're going to roll it 5 times and observe the number on the top. How many possible outcomes are there for a 5-sided die? Okay, I'm sorry, 16-sided die. So we're rolling it 5 times. So the first time I roll it could be 16 times. I pause that to look for, so I have some different die. I don't have a 16-sided die, but here's a 20-sided die, and here's a 12-sided die. Okay, so if I roll that, pretend it's 16 times, so how many different numbers could pop up, right? Okay, so the first roll could be one of 16 numbers. The second roll could be one of 16 numbers, and third, fourth, and fifth could be one of 16 numbers. So there would be, that many. 1 million, over 1 million different combination of numbers that could happen. Okay. Okay, part B. How many outcomes in part A do the 5 rolls produce 5 different numbers? Okay, 5 different numbers. So if you could do it 2 different ways. If there's 5 different numbers, the first number could be one of the 16 numbers. If one number has already been used, the next one could be one of 15 numbers. And if 2 numbers have been used, the next one could be one of 14 numbers, and 13 and 12, and you can multiply those together so you roll it 5 times. Another way to think about that is the permutation, where the order is important. So 16, choose 5, gives you this number as well. Okay. Number 7, I think they had a little misprint here. What's the probability that at least one of the rolls are the same? Okay. So we can think about this as the number that are the same. So we could have 0 or 1 or 2 or 3 or 4, all right, or 5 the same. So I could find these other and add them together, which will be a lot of work, but let's use a complement idea. So 1 minus the probability that none of them are the same. Okay. So the probability that none of them are the same, this is the probability that they're all different, right? That means that none of them are the same. And this is the number of how many total roles there are. So that gives us this number right here. The probability of none of them being the same number would be that number divided by the total number of roles. Okay, which is this number, which is almost 50%. So 1 minus 50% gives you 50%. So this is this number, 0.4999, and all these added together would be right around 50% of the time. Okay, number 8. Okay, Mr. Baker, I don't know how to say his name. Anyway, often uses a computer program to randomly select 4 students from his class of 24 to solve a problem on the board. How many possible teams of 4 students can be created from this class? So, in this case, we're thinking that order is not important. I'm selecting 4 people. So it doesn't matter if you're selected first or second or third or fourth, you're still being selected to come to the board to answer a question. So that means the order is not important, so it's a combination. It's 24 taken 4 at a time, which is a little over 10,626 different ways that we can get 4 people out of 24. Okay, part B and C was a little harder. One day, he poses a particular challenging problem. In his random number generator, produces a team of 4 students that include 2 of the top 3 students in the class. What's the probability that our randomly selected group of 4 students will include 2 of the top 3? Okay, so the total number of ways that we can choose 4 students is this. Okay, so the probability of getting 2 of the top 3 would be this probability. So there's 3 ways I can select 2 of the top 3, and out of the total number of possibilities, which gives me this. So part C then says, based upon that answer, do you suspect that he rigged the random number generator? So it's quite possible because the probability is really low. So he might have rigged it so that the top ones are there. But every answer is a possibility.